Welcome back. We're going to take a look at applications of some of these linear first order differential equations. And one very cool, kind of important application for us is mixture problems. And so these ideas are, what would happen if you had this container full of this, let's assume it's a liquid, that has a mixture or some sort of solution in there, like salt or pollutant or acid or something in there. And you're not only are you pumping stuff into it with a different concentration, but stuff is also leaving it, and it's really mixed up, so it's very good. So the concentration leaving is representative of the concentration of the tank in that moment of time, so it's very well mixed. Well, these problems ask, how long would it take to get a certain concentration in the tank? Or what would the concentration in the tank be after a certain amount of time? So we're going to take a look at 3 examples on how to do these types of problems. Kind of cool, and they all revolve around these linear first order differential equations. So let's take a look about what we're going to be doing, and then take a look at our examples. So mixture problems, how the solution changes over time, which is what differential equations study in the first place, is how things change over time. If X is our solution, so the amount of the solution at a certain time, so that instant of time, how much salt is there, how much acid is there, how much pollutant is there. Well, let's try to model this. So I'm going to walk you through where these equations come from, because sometimes when you look at this in the book and you go, what does that mean? Let's see how that's created. So if we think about how much solution, so X, the amount of solution, is going to be in our tank after a certain amount of time, well, that really relates to how much we're putting in and how much we're taking out. So firstly, let's think that the change of the amount that's there over time would be a change, an incremental change of that amount over time. Well, what would that be equal to? How do you see the change of how much is in there? So we have this tank of stuff, and it's got a certain mixture, let's say, I don't know, 5% salt or whatever, and you're going to start pouring stuff into there, another concentration. It's going to start changing how much salt is in the tank. So this idea is, imagine that you have this vat of stuff and it has a certain concentration. You start pouring in this other solution that has a different concentration. What's in your tank is going to change. If you start pouring in a weaker solution, it's going to start having a weaker concentration. If you start pouring in a stronger solution, it's going to have a stronger concentration. And let's also imagine you're pouring something out. So at every moment in time, you're getting additional, your concentration is changing in your tank. It's either you're gaining some of this amount or you're losing some of this amount of whatever you're talking about, salt or acid or whatever. Well, how that's changing, if we can make this change equal to something we can understand, and if we can make this into a differential equation, then by solving the differential equation, how the solution is changing over time, we can find an equation for the solution itself. Do you guys see what I'm talking about? So this right here would be the change in solution. We're wanting to find a function for the amount of the solution. So let's think about how this would change. You know what I'm going to do is I'm going to walk through what's called a verbal model. If you've watched all my videos, which means you've watched like 1,000 videos, you've seen me do verbal models for word problems a lot. That's how I always start them. So how would we look at how our actual amount of solution is changing? Well, it really would be a difference in the amount that you put in minus the amount you take out. Well, that should make some sense. I mean, we have the way that our amount of salt is changing is pretty closely approximated with how much we are pouring in of the salt, so the mixture we're pouring in, and the mixture we're pouring out. The difference between those two things is how our salt is changing. Notice how this is not how much is there. It's how it's changing. So the amount of salt that you start with, that's in there. And that would stay completely consistent. If you didn't pour anything in and didn't pour anything out, this would stay exactly the same. How it's changing is a comparison of how much is actually coming in minus how much you're actually pouring out. That's got to make sense before we go any further. So amount in minus amount out is not how much is there. Amount in minus amount out is how what's there is changing. How what's there, the amount of the solution, is changing. Now let's talk about the amount in, amount out. That's going to depend on two things. The amount of salt that you're actually pouring in, so the salt in what you're pouring, the salt of the concentration that you're pouring in, it depends on how fast you're pouring in and what the concentration of what you're pouring in is. For instance, let's say that you're pouring in this salt solution, we call it a brine, pour in a brine at 1 gallon a minute. Well, if you pour in at 1 gallon a minute, and let's say it's 5% salt, that would be like it's just a real pretty mild salt solution. You pour that in at what I say, 1 gallon a minute, or versus 5 gallons a minute of the same solution. Well, you'd gain salt a lot quicker pouring in at 5 gallons a minute than you would at 1 gallon a minute. Also, you'd gain salt a lot quicker if you poured in a 50% solution versus a 5% solution. So the amount in is really a function of two things. It's a function of the rate at which you're putting it in and the concentration of what you're putting into that tank or reservoir or vat or whatever you want to consider. So the way that the amount of our solution is changing is the amount in, but that's a rate times a concentration times a time. How fast are you putting it in? What's the concentration of what you're putting in? Which means this, what percent, what proportion of what you're actually pouring into this vat is really salt or acid or pollutant, times how much time you're putting this in. So this is a rate in, a concentration in, and a time for how long you're actually pouring that in, minus how much you're pouring out. So we're not just pouring in this situation, we're actually letting fluid, let's assume it's fluid, leave the container. Well, the amount out would be same idea. How fast are you letting this drain out? What's the concentration of what you're letting drain out for how long you're doing it? Well, that's another rate times a concentration times a time. Well, let's keep on going. Let's call these things some variables. Right now what I've done is I've just done a verbal model. And man, I hope it makes sense. I'm going to recap it here in just a couple minutes, but keeping on going, let's call the rate in R sub I. Let's call the concentration C sub I. And let's call the change in time this incremental change in time. What's happening if I look at the change in every quarter second or tenth of a second? Minus rate out, R sub O, concentration out, and the change in time, delta T. Well, we got to look at a couple things before we go any further. First is whether you understand it. And second is, what of these four things are constant? Which of those four things are constant? So first thing, we're trying to model a changing amount in a mixture. How we model a changing amount in a mixture, it's going to end up being a differential equation. What we want to do is create a differential equation so that when we undo that, when we solve that differential equation, we find a function that would tell us the amount of that substance in the tank or vat or whatever at a certain amount of time. This is our goal. Our goal is find an equation that will tell us how much is there at a certain point in time. How are we going to do it? Well, the only thing we know about right now is how it's changing. How is that amount changing? Well, the only way that that amount can change is if I'm pouring something into it or draining something out of it or both. And the way that would change would be you're adding something, some amount of solution, and you're taking some out. Well, how much you're actually adding, so the rate of change of our salt here, let's call it salt for now, the rate of change of our solution, our salt, would be, well, the rate of how much you're pouring in times the concentration of what you're pouring in minus the rate that you're pouring out times the concentration you're pouring out. This has to start making some sense to you right now. This is the amount of salt that you're actually getting in. This is the amount of salt that you're actually getting out. So we're calling those variables, and now let's talk about what are held constant. Well, we're going to hold rate in constant. Why? Because it's really hard to do without that. It'd be like this. It'd be like, hey, hey Jim, I want you to pour this solution in. Like let's say it's a 5% salt solution. I want you to pour this 5% salt solution in at like 5 gallons a minute. And you go, okay, no problem, man, I got that. So it's pouring in 5 gallons a minute, and you go, hey Jim, you still pouring that at 5 gallons a minute? He goes, no, now I'm pouring it at 2. Why? Because I wanted to. You go, dude, you just screwed everything up because my math is now off. So I have to have Jim pouring in that solution at 5 gallons a minute for the entire length of this problem. Otherwise, we'd have to do several different problems and add them all up together. Okay, so that rate in, we're going to hold that to be constant. Also, the concentration in. If Jim's pouring in a 5% salt solution and then he just decides to change it to 25%, that's going to drastically affect our math for how much salt's actually in there. So we're going to hold the rate in at constant and the concentration in at constant. The other thing that we're going to hold at constant is the rate out. So if you open the floodgate to a lake, or you open the valve on a tank or something, we're going to assume that that's pouring out at the same rate all the time. Otherwise, for the same thing like Jim's pouring in at 2 gallons a minute versus 5, it's going to really be too hard for us to solve with this model. Could we do it? Yeah, but we'd probably need several several different scenarios and add them all up to do that. So we don't want to do that. So for our examples here, we have to hold the rate in at constant. You're pouring in at the same rate. We have to hold the concentration in at constant. What you're pouring in all has the same concentration. And then we have to hold the rate out. What's leaving the tank, how fast it's leaving the tank is constant. What's not constant, what we can't hold constant is the concentration out. You see, unless the container and what you're pouring in has exactly the same concentration, what you're pouring out is always changing. If you have this pure water and you start pouring in a concentration with salt in it, this is going to start getting more and more salty until you start draining stuff out. So that concentration out is always changing. Now, there is one thing we're going to assume about this. We're going to assume that in this vat or this lake or whatever is very well mixed. So there's this mixer going crazy. So as soon as you add something to it, it's immediately perfectly mixed. Realistic? I don't know. Otherwise, remember that trade-off we have in differential equations where we want to make it practical but doable. This is one of the things we have to assume to make it practical. And doable. Otherwise, when we start considering that it's not well mixed, we have different concentrations in the same vat, very hard to deal with. So rate in held the same. Concentration in held the same. I hope you understand why. We kind of have to do that. Otherwise, we'd have several different problems we'd have to add up. Rate out held the same. So you're letting it drain at the same rate, but the concentration out, it is changing because what you're adding into it and what you're pouring out of it affect how much is actually there. Let's talk a bit more about that, the concentration out. If it's not constant, what's it based on? What would the concentration out be based on? How you find a concentration all the time is you compare how much salt or how much actual contaminant, pollutant, salt, acid is in the container divided by how much volume is in the container at that time. Now, what do we mean about at that time? Well, in your container, the volume's only going to stay the same if we're pouring in and we're pouring out at the same exact rates. So if R sub I equals R sub out, R sub O, then yeah, your volume would be constant. And we're going to see that in the very first two examples that we do. But if your rate in is quicker than your rate out, your volume's going to change. It's going to grow. If your rate in is slower than your rate out, our volume's going to decrease. It's going to change and it's going to get lower. So our concentration out is based on two things. How much actual salt or solution is there divided by the volume that you currently have at that moment of time. So the concentration out, well mixed, sure, but always changing. It's based on how much is there divided by how you're distributing it in this volume at a certain amount of time. Let's go ahead and let's change this. Let's change this and just put C sub O. Let's make that X over V. So amount, how the amount in is changing minus how the amount out is changing. But the amount out, rate out's the same, concentration out is X over V with respect to T. Man, that looks a whole lot like stuff from Calc 1. I wonder if we could divide everything, so both sides by delta T. Since delta T is not zero, so delta T would be a legit change in time. You're not dividing by zero here, you're saying after seconds or days, little teeny bit. That means we're not dividing by zero. And we would get an approximation for how the amount of the solution is changing over time, an incremental change, little by little by little, by very little. When you deal with incremental change, what you're getting is an approximation. This goes all the way back to Calc 1. If we're looking at little chunks of time, so after this amount of time, and this amount of time, and this amount of time, we're missing the ability to give instantaneous amount of time because those chunks, maybe what you're measuring falls in between the amount that you're actually considering here. What solves that for us is a limit. Do you remember? Man, I hope you remember. Remember limits, how what happens with that increment is that gets really close without becoming zero. And it says that, well, those increments, if they're getting smaller, you're getting more and more accurate measurement, and that limit lets us do that. So instead of delta x over delta t, we start taking limits and we change this to a derivative of x with respect to d, a differential. And then it's no longer an approximation. That limit says, man, you're so close together, it makes no difference. It's still not zero, but it's so close that you're no longer approximating. Our theories of calculus that we studied in Calc 1 tell us that this is now exact. I've dropped the respect to t because this says it. The derivative of x with respect to d. Oh my gosh, a differential equation, a first order differential equation, look at your independent variable. It's t. Look at your dependent variable. It's x. You have x to the first power. And you have a function of t, your independent variable. Sure, x is also a function of t, but that's taking the place of our y like we did in the last video. We had dy dx, and then we wanted to see y to the first power. Now we have dx dt. We want to see x to the first power. This is a first order differential equation. It happens to be a linear first order differential equation. If we just add this to both sides, and maybe this will help you see it a little bit better. We have equation, differential equation, first derivative, so first order differential equation, linear. We have our dependent variable right here raised to the first power. What's in front of that? A function, that's a function of t. A function of our independent variable equals functions that are constant. That's cool. This is a linear first order differential equation. We're going to use exactly the same techniques to solve it. My whole goal for this first part was just to get you familiar with the formula, because sometimes we're given that and you go, that looks like crap. I have no idea what's going on. Here's what's going on. Hopefully I've done a good job of explaining what's going on with these mixture problems. You're trying to find an equation that gives you how much salt is in a vat with respect to time. If we solve this differential equation, we're going to find an equation that gives us how much salt. So we'd find x of t, how much salt is in the vat after a certain amount of time. How we're getting around that idea of solving that directly is saying, well, I don't really know how to solve it directly. Let's find a differential equation. Let's look at how that salt is changing. Well, the amount of salt is changing in that we say how much we're getting in minus how much we're getting out. Okay, how much are we getting in? How's the amount we're getting in changing? Well, that would be the rate in times the concentration, how fast you're pouring in and the concentration of what you're pouring in, minus how fast you're pouring out and the concentration of what you're pouring out. That difference there would be how that salt amount is changing. Okay, cool. Let's call it some variables. Let's look at what's constant. You're pouring in at a constant rate. Constant. Your concentration of what you're pouring in, not changing. Constant. The rate at which you're pouring out, constant, not changing. The concentration of what you're pouring out can't be constant unless what you're pouring in matches exactly what you're pouring out, and then this is a very boring problem because nothing ever changes. You're like, give me 30 of those, please, so nothing changes. That's just done. That's the way it works. So the concentration out would be, in that moment of time, how much does that vat have in it? How much salt is in that vat? Divided by how much volume is in that vat at that moment of time. Notice if your rate in and rate out are different, the volume is growing or decreasing. The amount of salt that's in there is always changing if your concentrations are changing. So the concentration out, what's leaving your tank or your vat, is a comparison of how much salt's there divided by how much volume is there. That's the concentration. That's how we find the concentration for everything. So let's put that there. Okay, we got that. Now, that looks a lot like we could divide by the increment of t. Divide by delta t. Okay, cool. Now, we have an approximation for how the salt is changing over time. Let's do a limit. Let's do our calculus 1. That's now a derivative. The way that x is changing with respect to time instantaneously is how the amount in is changing minus the amount out. We have that down. Then we subtract on both sides and we get a linear first order differential equation. And that's where that formula comes from. I'm going to erase the board and we're going to do 3 examples. We're going to kind of go from easy ones to some harder ones and then we'll call it good. So now that we have, hopefully, a good feel for how a mixture problem is going to work, let's look through 3 examples. So the first one, very basic. We're just going to get our feet wet with this. No pun intended, we're talking about water, sugar water here. But what I'm going to do is I'm going to start with this in this example and show you how that comes about from it. So I'm going to kind of repeat myself a little bit here because I really want you to get the idea. It is worthless for someone to be able to do the math without understanding what's behind it. So let's look at the situation. We've got this 1,000-liter tank and it's really well stirred. So if we put something in there, we're going to assume that it's stirred up perfectly, like instantaneously. We've got a 1,000-liter tank and it contains 100 kilograms of sugar. So it's this mixture that has 100 kilograms of sugar in 1,000 liters. Well, that's a concentration, isn't it? Now, we're going to pump in some pure water. So Jim's been messing up today, all right? He put in 100 kilograms of sugar instead of 10. So Jim just way overdid it with the sugar. He's a sweet guy, but I mean, come on, all right? So we got 100 kilograms, we want 10. So what Jim's going to do, he's going to drain some of it, but he doesn't want to start over. So he's going to drain some of it and he's going to pour in pure water. What's that going to do? If you start pouring in pure water and draining out what the current concentration is, well, then you're going to start losing sugar, aren't you? You're pouring in something pure, you're taking out something that has sugar in it. Your concentration is going to drop. Our question is, how long is it going to take for us to get this mixture that has only 10 kilograms in the tank? So we want to find a formula. Again, suspense is not good for math. So we want to find a formula for the amount of sugar and set it equal to 10. Then we can solve for t, how long that's going to take. Let's start by identifying what our variables are. We need to know a rate in, a concentration in, a rate out, and something for the concentration out. So let's talk about the rate in. Rate in is how fast are you pouring in the whatever you're pouring in. In our case, we're pouring in this pure water at 5 liters per second. Let's call that 5. Our units match up. We're talking about liters, so we got 5 liters. Great. Seconds. So when we solve this, our T is going to be in terms of seconds. What else do we know? Well, the concentration in. Concentration in. We're pumping in pure water. How much sugar is in pure water? Well, if it's pure water, nothing, no sugar. So how much actual sugar is being put into this? Nothing. 0 sugar in what we're putting in, so the concentration will be 0. How about the rate out? Rate out is also 5, so whatever this mixture is at that moment in time, we're pumping out 5 liters per second. Concentration out, we don't know what that is. So as far as the concentration out, no, it doesn't say what that is. In fact, that's part of this problem here, is that concentration is always changing. So let's think about how that's changing. How the concentration changes is how much sugar is in there at a moment in time divided by how much volume is in there. And that's not changing because what we're pouring in, what we're pouring out is the same. Does that make sense? That if you pour in 5 liters per second into this 1,000-liter tank and you take out 5 liters per second, at any moment in time, you're still going to have 1,000 liters. So our concentration is X over V. Our X is going to change with respect to time, but let's think about our V. Our V, we just mentioned it. If you've got this 1,000-liter tank, you're pouring in and taking out at the same rate, that volume is constant. So our volume here is just going to be 1,000. Well, let's start putting this all together. If we take our variables and plug them in down here, R sub I, that's 5. C sub I, that's 0. Minus R sub out, 5 times C sub out, that's X over 1,000. If times how much time is changing. If we divide both sides by delta T, notice how this whole thing is 0? That's completely gone. Well, we would get delta X delta T is equal to negative 5X over 1,000. That's an approximation. That's about right. If we let our calculus work for us, we get a differential equation. And if we add that to both sides, oh my gosh, we got our dependent variable, we have an x here. Let's make sure our x is with our dx over dt. Equals 0. The only reason why I did this, I'm not going to really do it after this so much, is to show you that what you get from here by just using your logic of in, out, and all that stuff, and the x over v, is exactly what you get here by what most textbooks would give you as a formula and say, just use this. Why? Because we know how to deal with Calc 1. That's why. But check it out. Could you actually get the same exact thing? Sure. You got a dx dt, got a dx dt. You got the rate out. The rate out is 5. Rate out is 5. You get the volume, volume's 1,000, volume's 1,000. You have an X, you got an X. You have a rate in times concentration in, that's 5 times 0. Oh, you got a 0. Same exact stuff. Now comes our knowledge of, hey, that's kind of cool. This is a linear first order differential equation. Can we solve it? Sure, we know how to do our integrating factor of rho x. We know that that's going to be e to the integral of whatever's in front of our x. I prefer writing like that, where we'd have five over 1,000. You might even just do 1 over 200, so that might be a little bit nicer. And we know all about this. I'm not going to recover it again because I've done that many, many times, but this is the result of a product rule. We're trying to multiply everything by something that's going to show that. So how that something works, you want something that repeats, that's e to the whatever the integral of this is. This has to be the derivative of that exponent, so 1 over 200. I also made a little bit of a mistake. It's right here. That should be a t, because this right here needs to be a function of t, not x. And it's going to happen to you too. You're going to start putting the x everywhere because we're used to that being an independent variable. It's not here. It's t. So we're going to find rho of t. That's going to be e to the integral of 1 over 200 dt. Well, that's just going to be t over 200. We don't need a plus c, that's totally fine, no big deal. And if we multiply everything by that, so we have a dx dt, no problem. We've got a plus 1 over 200, and we have an equals 0. And if we multiply both sides by e to the t over 200, we don't want to forget our x. On the right-hand side, 0 times anything is 0. On the left-hand side, this is now the result of some sort of product rule on a product. And let's double check. Is this the derivative of this? And sure enough, it is. E to the t over 200 comes back. The derivative of t over 200 is 1 over 200. We have our x. So this is the result of some sort of product rule, which we're going to write over on the right-hand side. So the derivative with respect to t of this product we're getting, this piece, this would, on a product rule, the first does not get a derivative. So this is a result of something not being, kind of mumbled that one, thinking too fast. This is the result of that product rule where we don't take a derivative of the first factor. This is the result of the product rule where we don't take a derivative of the second factor. So that's going to be our x. On the right-hand side, we get 0. Now, if that's the derivative, then an integral is going to undo that derivative. Let's do an integral with respect to t on both sides. On the left-hand side, integrals undo derivatives, no problem. We get e to the t over 200 times x. On the right-hand side, we don't get 0. Remember that this is with respect to t, sure, but you're going to have a c, a constant. Now it's about time for us to use an initial value. Like I'm not giving an initial value. You sure are. The very first sentence says a 1,000-liter tank that contains 100 kilograms of sugar. So at the start, that's what this x of t means. This x of t means how much sugar is in there at a certain amount of time. So for us, well, at time 0, we have 100 kilograms of sugar. So remember what we're doing. We're trying to find a formula that tells us how much sugar is in that tank at any given time. At time 0, we had 100 kilograms. So if we plug in t equals 0, x has to be 100. E to the 0 is 1, 1 times 100 is 100, c equals 100. And if we rewrite that, we're going to get something that we can easily solve for x. So I know that we kind of switch variables around, and instead of y, we have x as our dependent variable, but that's kind of the idea of working with that x, is that that x should be this equation that says how much the amount is of whatever our solution is over a certain amount of time. The way we're structuring this is, let's think about how that solution is changing. Well, that's solution in minus solution out. Gives us a nice differential equation. We solve it. We solve the differential equation, which represents how the solution is changing, and find out the amount of the solution at a given time. That's great. Let's multiply both sides by e to the negative 200, t over 200, and we would get x of t equals 100 e to the negative t over 200. Why negative? Does it make sense that the exponent is negative? You have a vat of sugar, and you're pouring in pure water. You're also draining out the solution. You're draining out sugar. This right here should decrease. Our sugar amount should decrease exponentially. It's exponential decay. That's kind of cool. Do you see the interplay between how our sugar's changing and the amount of sugar in the tank? So how are sugars changing? That's a differential equation. It says the amount of sugar, how that amount is changing is out in minus out, no problem. When I solve the differential equation, it's giving me the solution for how much sugar is actually in there for a given amount of time. That's it. Now we can answer the question, when? When's the time? When will there be 10 kilograms? Okay, if x represents how much there is, when will this equal 10? That's what we're asking. So when will there be 10 kilograms? Solve for the time that gives us 10 kilograms. If we divide both sides by 100, if we do an ln on both sides, and if we multiply both sides by negative 200, oh, what did I get? About 460 seconds. How I know it's seconds is because that was what our T was defined for. So this was 5 liters per second, so that change is also in seconds. Man, I hope that makes sense. I hope it makes sense that we're really relating this, how our solution is changing, to a differential equation, and then undoing that to find what our amount is after a certain amount of time. It's pretty cool that we can even do it. We see an integrating factor, just like you do with any linear first order differential equation, and then we can solve by understanding that, yes, we have an initial condition, initial value, and then when we modify our function that we found, we can typically either find how much is there after a certain amount of time, or how long it's going to take for us to get that amount. And that's what we did in this case. So we've got 2 more. Let's work on them now. Let's start a new problem. So you have a swimming pool, and through someone's error, Jim's, you have this pool that's 8,000 cubic feet of water, but it has a 25% chlorine solution to it, concentration. That's a lot of chlorine. So the kids are getting out, my eyes, and man, come on, Jim. So you decide that you're going to just change it over time, and you're going to add 500 cubic feet of 5% solution. Why would you add pure water? Maybe you live in a town that has like a lot of chlorine in your water, and like, it's about 5%. So you add 500 cubic feet of 5% solution a day. So just putting a hose in that, hopefully you're going to drain this water somewhere else and not waste it. And you drain the same amount. So you're going to drain out exactly the amount that you put in. Question. What is your volume going to do? Is your volume going to change, or is your volume going to remain constant? If you're adding and subtracting the same amount, so pouring in, pouring out the same amount, it's going to remain constant. So when will there be a 10% concentration? Let's go ahead and figure this out. So the first thing we want to do is identify what's the rate in, what's the rate out, what's the concentration in, what's an expression for the concentration out. The rate in says that we have 500 cubic feet of 5% a day. So whatever we get out of this, our time is going to be in days. So rate in 500. Rate out 500. No problem. It says out of the same amount out, so that's the same rate out. Concentration in says we have 5%. Let's make that 0.05. We know percentages work like that for decimals. Concentration out, we don't know. Let's work on that in a minute. But the volume, because we're adding in and subtracting out the same amount, our volume's always going to be 8,000 cubic feet. Now the concentration out, what we've been learning is that the concentration out is a relationship between how much chlorine's in there divided by the volume of our tank. Or in our case, how much chlorine's in there divided by 8,000, because that volume isn't going to change in this scenario. Let's start putting that into our differential equation that we know we're going to get. So dx dt, how are chlorines changing with respect to time? Notice this is how it's changing, how chlorine's changing with respect to time, the rate of change of chlorine with respect to time. If we undo this derivative, we get the amount of chlorine with respect to time. That's the idea, the position of the chlorine, how much we have. So the rate in says we're going to have, okay, 500 times the concentration in, that's 5%, minus the rate out, that's 500, times the concentration out. That's how much is there compared to how much we have. How much chlorine's there compared to how much volume we're taking out. That's always going to be 8,000. Well, let's simplify some things. Looks like we get 25. That's 25. Yeah, 25 minus 1/16 x. That is a linear first order differential equation. If we add 1/16 x to both sides, we now have something that we can work with. I would encourage you to try it on your own right now. If you haven't tried it, try it. Man, stop the video. Figure out what your integrating factor. Figure out what row of x has to be. Integrate 1/16. Take e to the integral of 1/16, and then multiply that everywhere. We're going to do it now, but you might want to pause this and try it on your own. So for us, rho t, so this is with respect to time, is e to the integral of 1/16 dt. That means that we're going to get e to the t over 16. Really similar to the last problem. The only difference here is that we had a concentration in that wasn't zero. Let's multiply that everywhere. So we have e to the t over 16 dx dt. We've got 1/16 e to the t over 16, which is really clear to see that this is the derivative of this. That's great. That's perfect for us. Times x, we don't want to forget that, equals 25 e to the t over 16. Also in this case, because we had a concentration in, this isn't zero. Now, what we do know about these differential equations that are linear is that this is the result of a product rule on some derivative with respect to t of this term times that term. This factor times x. That's then leave the first alone, derivative of the second with respect to t. Cool. Derivative of the first with respect to t, got it. Leave the second alone. Not a problem. On the right-hand side, we have exactly the same thing. And this lets us take an integral with respect to t. On the left-hand side, integrals undo derivatives. That's awesome. We get e to the t over 16 times x equals, on the right-hand side, well, let's see, we'd have u equals t over 16. So we're going to have to multiply both sides by, or we're going to have to multiply by 16. So if u equals t over 16, du equals dt over 16, that means 16 du equals dt. So let's put that in there. 16, 25, let's see, 4 times 25 is 100, times 4 would be 400. Plus c. You can do a couple things right now. If you really wanted to, you could solve for that x, but I would solve for c right now. So solving for c, you're going to have an initial value. Now, a lot of times it's not specifically given to you. You got to find it in a mixture problem. So let's go back to the beginning. It says we've got a swimming pool, and our pool has 8,000 cubic feet of water, and it has a 25% solution of chlorine. Do you realize that at this point, we have an equation that's giving us the amount of chlorine? It's not the rate of change of the chlorine, it's the amount of the chlorine at a certain time. How does our chlorine start? At the start of this, at time 0, the amount of chlorine says, well, you had 8,000 cubic feet times a 25%, 0.25, times a 25% concentration. What that means is that the amount at time 0 was how much total fluid you had, but there's only 25% of it is chlorine. Multiply that. Man, it better make sense to you right now that at the start of this, in your swimming pool, there's actually 200 cubic feet of chlorine, if that's 25% makeup of that pool. So 8,000 cubic feet, 25% of it was chlorine. That means that you have 8,000 times 0.25, that's 2,000 cubic feet of chlorine. So much chlorine. That's 2,000 cubic feet of chlorine. That's your initial value. So if we plug in 0 for t, we know that x is 2,000. One times 2,000 equals 400 times 1 plus c. c equals 1,600. And if we augment this, we get let's see, 400 plus 1,600. Now, let's multiply both sides, which means all three terms, by e to the negative 16, e to the negative t over 16. This will be gone, this will be gone, this will gain an e to the negative t over 16. Okay, I'm going to walk through this one time with you. We start off with labeling everything that we possibly can. We understand that we're creating a differential equation which gives us the rate of change of the chlorine with respect to time. Solving that differential equation says now we're no longer talking about the rate, we're talking about the amount of chlorine with respect to time. That's given by this standing from our initial value, saying we had 8,000 cubic feet of water, okay, 25% of it's chlorine. That's 2,000 cubic feet of chlorine that we started with. So we set that equal, and then we solve, we get a function that says this right here is going to tell you how much chlorine is there with respect to time. Now we answer the question, how long is it going to take? Find the t. How long is it going to take? Find the t. Until there would be a 10%. Now, we are taking out the same amount of fluid, same amount of mixture here. We want 10% of this to be chlorine at the end. So we want the amount of chlorine to be 10% of the volume of the fluid. Okay, how much fluid's in there? What's the volume? Has it ever changed? No, it's 8,000. So we want 10% of that to be the amount. So if x of t represents the amount of chlorine that's actually in there, we want 10% of 8,000 to be chlorine. Does that make sense to you? I hope that makes sense to you. But you go, all right, well, for here, I want 10% of my volume to be chlorine. I want 800 cubic feet. So the question comes down to, and this is why I'm doing this example, is because when you get the concentrations and percentages, you're going to have to multiply by the amount that's there. So to find your initial value, 25% was chlorine. Okay, multiply by 0.25. You want 10% to be chlorine. Okay, multiply what's there, 8,000 times 10%, 0.10. That gives you want 800 cubic feet. So the question boils down to, if this shows you how much chlorine's actually there for a certain time, we want to find out when this is going to equal 800 cubic feet. So when is our chlorine, X, going to be 800? And that's pretty easy to solve. I'm going to encourage you to do it on your own. We'd have to subtract 400. We'd have to divide by 1600, so you'll get 400 over 1600, that's 1/4. Take an ln, so ln of 1/4 equals negative t over 16 multiplied by negative 16, so t equals negative 16 ln of 1/4. What's our t in? Minutes, hours, years, days? Well, because we're draining this in per day, this is going to be about 22.2 days. Is it making sense to you? I hope it is. I hope that you're understanding the relationship between differential equation is the rate. Undo that, you find the amount. That's so cool. And we're just using the techniques that we've already known. We have one more problem we're going to go through, a little bit more advanced because our volume's going to be changing. I have to show you how to do that, and then we're going to be done. Okay, one more. So we have another situation. We've got this tank of a brine solution. Now, it's a 400-gallon tank, but you have it 100 gallons full, so it's not full, of this brine with 50 pounds of salt in it. So you probably add some water and you put in 50 pounds of salt, and you're going to fill it up with this other brine until it's full. So the question is, if you add brine that has 1 pound per gallon, and you're filling this at 5 gallons a second, and you're outflowing it at 3 gallons a second, how much salt is in the tank when the tank is full? We're going to go ahead and do this problem, but before we even start it, I want to ask two questions. Number one, I want to ask, what's the expression for the volume in the tank? Because this volume is changing. It's not like the other two examples. This is probably the biggest part of the problem here is the volume, and then when is the tank full? So let's do the volume first. As far as our volume is concerned, our volume starts at how much? How much is there when we start the problem? Well, we have 100 gallons right now. Now, look at what is happening. We're adding at 5 gallons a second. We're subtracting at 3 gallons a second. If we're adding more than we're subtracting, our volume is increasing. So it's not subtracting, it's adding. How much is it adding per second? Well, we have 100 gallons in there right now, but we're going to add 5 gallons in minus 3 gallons out for every t seconds. You guys get that? We're in time right now. We're in time is for seconds. So let's start the situation at 0 seconds. So when t is 0, we had 100 gallons. After every second that passes, I've added 5, I've subtracted 3. That's a total of adding 2. So our volume is a relationship that says you have 100 gallons plus 2 gallons per second. That needs to make sense. Think through this right now. When you start, you have 100 gallons. And as every second passes, you've added 5, subtracted 3, added 5, subtracted 3, added 5. You're adding 2 gallons for every second. That's a big deal. So when we get to filling out our concentration out, we'll just have X over that. Now, when is the tank full? Well, if you are gaining 2 gallons for every second, how much do we need to gain in order for us to have a full tank? Well, we want to have 400 gallons at the end. Right now we have 100. So we need to fill up 300 gallons. How many gallons are we adding every second? 5 in, 3 out, we're adding 2. So when's this going to be full? So the time would equal 300 gallons divided by 2 gallons per second. Notice even how the units work. We'd get 150 seconds. These are two really important pieces of information that we want to do first. That way when we get to them later, we have the right stuff for us. So we got this 400-gallon tank. It's 100 gallons full. Great. Let's see. We have filling up 5 gallons a second in, 3 gallons a second out. That's 2 gallons a second. 300 gallons to make up. We have 2 gallons a second. That's 150 seconds. Volume. The volume is this relationship between we had 100 and we're adding 2 gallons a second. This is the same idea used in 2 different ways. So the next thing we're going to do, maybe we put our initial value right now too, that how much salt was there at the very beginning of it. So this 100-gallon tank has 50 pounds of salt. So before those last 2 examples, we did our initial value second. Now that we know we have to have it, we have our volume expression. We know when our tank is going to be full. We want to figure that out first. How much is the salt's in there when it's full? And then we need an initial value. So at time of 0, right when the start starts, how much salt? Remember, X is how much of the actual item is in there, how much salt is in there. The dx dt is how is that amount changing? When we undo that with derivatives, we get how much salt's in there. This is going to help us solve for our arbitrary constant. Here we go, let's see, 0, looks like 50 pounds of salt. I'm going to pause for just a second to make sure that you get this. So we had this situation where not only is our concentration out changing, our volume's also changing. So this is a little different than the previous 2 examples. We're saying here that we want to fill this tank up and we want to determine how much salt is in there when we fill it up. When we fill it up is going to be in 150 seconds. So when we get all done, we're going to be plugging in 150 for t instead of solving for t. We're doing something different. We're trying to figure out how much salt's in there after that amount of time. Now, we also know where we start. We need an initial value to solve for our arbitrary constant we're going to get when we go through our process of solving our differential equation. Lastly, our volume. Well, our volume is now a relationship. It's now related to our time. So let's fill out what we can. The rate in, well, we know that's 5. The concentration in, 1 pound per gallon is an appropriate concentration. You can use that. 1 pound per gallon. Rate out, that would be 3 gallons per second. Notice how we're in seconds. So what we get out of this is going to be seconds. This is all seconds. Concentration out. The concentration out relates how much salt is there with respect to time divided by your volume, which is always changing. Notice how this concentration are in the same relationship. This is 1 pound per gallon. This is X pounds per gallon of volume. So that's okay to have that as long as they have the same relationship there. Now we can start plugging in. This better make sense, that you're in at 5 gallons, you're out at 3 gallons. You have a concentration of 1 pound per gallon in, concentration of X pounds per gallon out. Let's plug this into the differential equation. You might want to try this on your own. Let's see. 5 times 1. 3 times x over 100 plus 2t. That looks pretty good to me. That's a differential equation. Oh, my dependent variable x is over here. I want to group my dx over dt with my x term. I'm going to make it look like that linear first order differential equation that we want with x off to the back. So this is my p. This is the thing I'm integrating. Now I'm going to find my integrating factor so that I can treat this like the linear first order differential equation it is. So what we're going to multiply by is e to the integral of nasty crap. It's not all that bad. We can pull the 3 out. We can pull the 3 out. We'd have, do it quickly, you should do it on your own. We'd have natural log of 100 plus 2t divided by the derivative of that u, because you have a u sub here. So u equals 100 plus 2t. Derivative would be 2 dt. Divide by 2. You're going to get 1 over u. You'll get ln of u, put it back, but then you'd be divided by 2. So all this works out to, which you should try on your own, would be 3/2 ln 100 plus 2t. I'm dropping the absolute value because time is positive. We're not going back in time. We're going forward in time, so we don't need that there. So the 3 comes out. You divide by 2 because that's a u sub there, and you have ln of 100 plus 2t. So Let's simplify this a bit because we can. If we move this as an exponent, we get what we're going to multiply by to create this result of a product rule. Is that. Let's go ahead, let's multiply that everywhere. So from right here, we're going to multiply 1, 2, 3 terms by this integrating factor, so it's going to allow us to create this product rule. Let's see if I did it right. Got this, we multiplied here, looks good. Kept this, multiplied here, kept my x, got my 5, multiplied here. Everything's multiplied by the same thing. I'll take a derivative. Imagine doing this. I'd bring down the 3/2. I'd leave this alone. I would subtract 1 from it. And we're about to do that when we simplify. And then I multiply by the inside, which is 2. So that's where our 2 is going away there. So if I simplify this, here's 1, here's 1.5. Now we can really see it. If I take a derivative of this piece, we've got 3/2, leave the inside alone to the 1/2, there it is. And then times the derivative inside by the chain rule, that gives us 2, which would get rid of the 3/2 part of it. We'd get 2, so we just get 3. Now, that's the result of a product rule. Let's write the product. Product is, you left this piece alone when that derivative was taken. You left this piece alone when this derivative was taken. Equals and now it's just a matter of integrating both sides with respect to t. Integrals undo derivatives, we have this 100 plus 2t to the 3/2 x equals, on the right hand side we go through the kind of the same exact idea. We can pull the 5 out, we have another u sub, we add 1 to our exponent. So 5, keep our inside, add 1 to the exponent, divide by the exponent, but also divide by the derivative inside. So our u would be this 100 plus 2t. Notice how when you take the derivative, you get du equals 2 dt. You'd have to divide by 2. So you have an extra 2 here because of that u sub. I hope this is making sense. You kept the 5. This would be u raised to the 5/2 divided by 5/2, but then also divided by that 2 plus c. Try it for yourself. Make sure you're doing that. So we will get 100 plus 2t to the 3/2 x equals, well, gone. 100 plus 2t to the 5/2 plus c. It might actually be, no, I'd solve for c. I'd still solve for c here. Without ln, I'm solving for c. So we need initial value. Oh man, hey, good thing we did that first. So when we have 0 time passed, we had 50 pounds of salt. We can use that now. This is the amount of salt after time. That's what solving the differential equation did us. Instead of rate of how the salt is changing, we have amount of salt. Pretty cool. So when we plug in 0 for t, we get 50 for x. So 0 to the 3/2 times 50 equals 0 to the 5/2 plus c. This gets a little crazy, but 100 plus 0 is 100, square root of 100 is 10, 10 to the third is 1,000, so this is 50,000. 1,000 times 50 is 50,000. Equals right-hand side, 100, square root of 100 is 10 to the 5th, would be 1, 2, 3, 4, 5, 5 zeros, that's 100,000. So C equals negative 50,000. So when we change it, I'm going to have to erase this. We get that 100 plus 2t to the 3/2 power times x equals 100 plus 2t to the 5/2 power minus 50,000. We are almost done. We're so close. All we've got to do now is solve for x. So when we solve for x, let's multiply every single term by 100 plus 2t to the negative 3/2 power. Negative 3/2 power is going to kill this off. It's going to subtract 3/2, and you're going to get a negative 3/2 over here. So we have x. The amount of salt after time is going to equal, this is completely gone. This, remember, you're multiplying by this to the negative 3/2. It's going to subtract exponents. 5/2 minus 3/2 is 2/2. That's 1. Minus 50,000 times 100 plus 2t to the negative 3/2. I hope you see what's going on. We multiplied actually by this thing. Here created 1. Here created this to the first, 5/2 minus 3/2. Here you had to multiply it, so it's got to be there. Man, that's nasty, but that's our result as far as our particular solution here. So we started off with a rate of change. We created a differential equation. We solved it. We got an amount. We got a function for the amount of salt after a certain amount of time. So what do we do now? Well, we want to know how much salt is in there when the tank is full. This is a different type of question than the last two. Last two was, how long would it take to get this amount of salt? Now it's, how much salt is there after the tank is full? The tank is full in 150 seconds. We already talked about that. That's why we did that. So if the tank is full in 150 seconds, we want to know how much salt is there after 150 seconds. Because at 150 seconds, that tank is going to be right to the brim. Anything past that is going to be overflowing. Anything before that, it's not going to be full. So full would be at 400 gallons. At 2 seconds a gallon, to go from 100 to 400 would be 150 seconds. So we want to know how much salt is in there. How much salt is in there when it's full after 150 seconds have passed. So we need x of 150 seconds. Oh, yep, yeah, it looks to me like we get about, see if you can do this on your own, 393.75 pounds of salt. We started in pounds, so our answer is going to be in pounds. We started in seconds, so we had to use seconds, not minutes, not hours. Wow, I really hope it makes sense. So we're at the last, this is our last example for applications here, but my goal for this video was for you to see the interplay between using a rate of change, like for a mixture problem, how our amount is changing with respect to time, and using a differential equation to find the amount from that. Because a lot of these questions ask amounts, but you can't get it directly. You've got to start with a rate and then do integrals with it for our differential equations. And that's pretty cool. I hope I've explained well enough how the rate of in and the concentration of in are constant, how the rate of out has to be constant, but how the concentration of out relates to the amount we have in there at a given moment of time compared to the volume that we have for a given moment of time. I hope I've explained how to find the initial values, how that's rarely given to you. You have to start with you have to read through the problem and find out what's actually starting. And then for our questions, we're almost always saying how long, so that's a time, will it take to get this amount of salt. So once you figure out your amount function, you set the amount and then solve for t with usually some ln's. Typically you don't have to, but usually it's that. So solving how long, that's a t, will we have this amount of salt. Or in this case, what's the amount of salt when this happens? After 10 minutes, after 100 seconds, after the tank is full. When's the tank going to be full? Tank's full after 150 seconds. This right here is kind of the key of the whole problem. Because if you don't know that this is necessary, you're never going to be able to plug in a T. So reading through the problem very carefully helps us identify these were key. I hope that made sense. Next time we deal with a couple a couple different techniques, which is super exciting. We'll talk about homogeneous equations, we'll talk about exact equations, Bernoulli equations, we'll talk about substitution techniques, all sorts of fun stuff. So hope you enjoyed this one. I'll see you for another video.